Okay, so what's on the schedule today?
Well, so first of all, I should admit that I don't have I didn't quite do my supposed homework, that I don't have the concrete reciprocity laws for the Z mod 3 torsors. I don't have those worked out yet, but I have I think, a list of, sort of good excuses for why not. And my first excuse is to claim that in principle, it is straightforward to develop this. And, we already know in principle how to do it. We just have to work it out at some point. And in fact, one of my other excuses is that, we could try to actually do that on the spot today or, some other day. But another one of my excuses is to claim that I have something better than the explicit reciprocity laws to try to talk about. So let me try that tack for the moment. So you might recall, I think it was probably the last time that we talked, and you pointed out to me that there was some visual motif that just showed up in two different places.
Yeah.
And the question arose as to whether it was a coincidence or not. And that visual motif was kind of that we had like a tic-tac-toe board, meaning like a two-dimensional vector space over a three-dimensional field. And we found ourselves thinking about this subspace and in contrast to the diagonal subspace. And I guess we also thought about the two axis subspaces, but somehow we found it more interesting, instead of looking at the axis subspaces, to look at these other two, the diagonal one and the, I don't know what we call it, anti-diagonal one, or I guess you were calling it the night move subspace. And so yeah, so when you pointed this out, well, let's see, what were the two different ways that it showed up? Yeah, it was hard for me to tell whether we really had it showing up in one way or two ways.
They seem really different, actually, to me.
They did seem really different, but I think they're not as different as they seemed at first.
Okay.
So one of them had to do with the idea that we were thinking about this sort of generic or somewhat generic Galois group when you first join the primitive cube roots of unity. So that's a quadratic extension. And then after that, adjoin some cube roots. And when you make it a Galois extension. So somehow I tried to convince us that that would correspond to the Reith product of Z mod 2 acting on, well, how do I say that? The Reith product of Z mod 2 and Z mod 3. That's one way to say it. But it's the semi-direct product of Z mod 2 acting on the Cartesian square of Z mod 3. And the Cartesian square of Z mod 3 is sort of showing up because there's an Eisenstein conjugate pair of quantities that you could take the cube root of in general. And then we noticed that there were some special degenerate forms of behavior that could degenerate into, depending on if you took the cube root of a special Eisenstein number. So let's see, I guess, right. So the diagonal, that corresponded to like the very abelian thing where, and that, right, that ended up being some peculiar thing like you have a number X or whatever we call it, and you take its you take its, let's see, you get an equation between an equation up to cubic factors between, well, I guess it's between x squared and x and the sort of Eisenstein conjugate of x. And that turns out to give the abelian degeneration of this Galois group. So it ends up being it ends up being the semi-direct product of Z mod 2 acting on Z mod 3 trivially. So it's really just the Cartesian product. Whereas the semi-direct product of Z mod 2 acting on the diagonal thing, that corresponded to, I guess, just x equal, am I saying this right? X equals x bar up to cubes. Well, so this was our first story about how the picture showed up. We were thinking about this wreath product showing up as a sort of generic Galois group, and then the generic behavior would degenerate into two special cases. So I guess the wreath product is actually what, an 18 element Galois group. 2 times 9. But then it has these two 6-element Z mod 2 invariant subgroups, which correspond to these two interesting forms of degenerate behavior. And right, so this one is a very abelian kind of degeneration, and this one is kind of, I don't know, maybe we should call it like the real or rational degeneration. And so, okay, that was the first context in which these pictures showed up. And then the second context, which sort of seemed coincidental at first, and it's sort of, it probably is halfway coincidence and halfway not a coincidence, was when we were doing what? We were kind of, we were drawing these like little tic-tac-toe boards, but giving them a different interpretation. And I think I would have like, right, I would have some prime, like for example, well, I think we actually had the prime 3 and the prime 7 or something like that. But I mentioned some other examples. I'm not sure I actually went into detail about them, but I had like 7 and 13 or something like that. And these would, let me see if I can remember how the one works with 9 and 7. So that's, let's see, it's something like 1, I'm sort of doing this Chinese remainder theorem type thing here. Let's see. So modulo 9, you would have, how does it work? 1, 2, 4, am I doing this right? 8, 7, 5. And I think mod 7 would be what? 1, 3, 9, but 9 is 2, and then 2 times 3 is 6. Yeah, that's 6, and then 4 and 5 or something like that. So there were these kind of congruence conditions, and we were playing around with specific. First, it was specific splitting patterns, and there was like a splitting pattern like this that would correspond to some particular Z mod 3 tensor according to the conjectured reciprocity law. But then we were kind of refining this data so that, instead of just being a splitting pattern, it would be a Frobenius pattern. So that would be like the kernel I guess I'll write it additively for right now for some reason. So you could have like 0 and 0 and 0, but then you would have orientation information for the Frobenius pattern, which would distinguish between the two cosets of this. So you could have like 1 and, am I doing this right? 1 and 1 and 2, 2, 2, like that, something like that. So anyway,
what did you mean by splitting pattern? Is it about which prime split?
Yes. Yes. I mean, but right. I mean, I think this is not where the magic word reciprocity comes from. The idea of a reciprocal relationship, but there is a kind of reciprocity here, right? That you can talk in terms of the prime splitting over the field, but you could equally well talk in terms of the fields. Well, the prime splitting over the ring, or you could talk about the ring splitting over the prime, something like that, and they really mean the same thing. So maybe I just should have answered your question. Yes, we're talking about the prime splitting over the ring, but you can think of it, maybe it's even better to think of it the other way, as the ring splitting over the prime or something like that.
And those, so you're saying that, but in some extension, the primes that you marked that are congruent to things that you've marked with a 0 split?
Yes, that's right.
And there's none that does it for the primes that are congruent to 1, or they're marked with 1 and 2. Those
are the ones that don't split.
Yeah.
Yeah. They equally well don't split, but they sort of, right? I mean, I guess this is the sort of, who do I credit for this? Is it Tolstoy or somebody like that? That the unhappy ones are unhappy in different ways, that there's a kind of a left-handed form of unhappiness here and a right-handed form of unhappiness here. And that's right. That was what I was supposed to do for homework. I was supposed to clarify how, these Z mod 3 torsors have this extra bit of information, this left-handedness versus right-handedness or whatever. But that's the homework I didn't really do. So, but what we did notice is this, this kind of funny visual resonance between this picture and this picture.
Yep.
And so I'm claiming now that it's a sort of not a complete coincidence, but maybe it's about a halfway coincidence, something like that. So I'm not sure how convincing you'll find my claim that this is not a coincidence, but I'm going to try to convince you of it now that it's not a coincidence. Well, I mean, so the stupid answer to why it's not a coincidence is because they're both involving linear algebra, or if you prefer, functional analysis over the 3-element field. And those are showing up for the same reason, secretly the same reason. I mean, I guess what I'm trying to say is that in this picture, we're kind of putting, in this picture, the duality between horizontal and vertical axes is, corresponding to the idea that we're supposed to have some Eisenstein number. Well, I guess it's like we have like 1 and I'll call it y, because I'm afraid that it might be a little bit different from x. So I'll call it y and y squared. And over here we have y conjugate and y conjugate squared. And here we'd have, y times y conjugate. And here we'd have, what is it? Y squared times y conjugate and stuff like that. So, I mean, right, the way that it's not a coincidence is just that in this example over here, we're kind of we've got this special thing where we have conjugate things on the horizontal and vertical axis. Whereas over, when I was having like 7 versus 13, there's no relationship between 7 and 13, as far as I know. They're not like.
Yeah.
So that's the way it's not a coincidence. That's the way it's not a coincidence. But there's more to say about this. Well, do you have any? Are you halfway buying that idea? Yeah, go ahead.
So in the first appearance of this pattern,
yes,
you can just say that subgroup of the 9-element group for vector space is the only non-trivial one that's fixed but not pointwise fixed. So that's like what makes it so exciting or something.
That's right. That's right. And basically it all has to do with properties under Eisenstein conjugation.
Yeah.
That's right. That's right.
But in the new appearance,
yeah,
I don't see that symmetry of the square plays any.
That's right. It doesn't.
Okay.
Or it doesn't play much. I mean, I guess the point is that there's still the 2 axis ones, which sort of play a special role, but they play separate special roles rather than being conjugate to each other. And the other 2 are just interesting that you can get them by mixing things together with 2 different phases, so to speak. So it's it's a little bit like there are phases that we're combining things together here.
No.
Phases in the sense that we have like a projective space and different points of the projective space. It's sort of the same thing, except with different phases mixed together or something like that, like in a qubit or something, except this is a qubit over a finite field. Okay. So, so like I say, this is the basic idea for why I'm glad you pointed it out, that it's not a coincidence. But there's more to say about this, I think, if I can manage to say it the right way. So I'm checking my notes here. So, yeah. So, okay, I got it right. I'm still not used to the idea of not having an infinite whiteboard, but I guess it's getting a little bit messy here, so I'll go to a new page here. But I'm still trying to refer back to everything that we remember from the first page and just keep a complete copy of the first page in your mind.
Yep.
Or try to, or something like that. So, so there's something interesting going on here. I don't understand what it is yet, but I'm claiming and trying to point out to you that there's something interesting going on here. And it's like, there's something that I already claimed was interesting, but I'm now realizing that it's even more interesting. And so what I already claimed was interesting, perhaps 1 or 2 sessions ago, was this whole idea that we were just mentioning, that the generic behavior of taking the cube root of an Eisenstein number, that the generic behavior degenerates in 2 oppositely interesting ways. It degenerates in this sort of abelian way and this rational way. And I may suggested that, well, it would be interesting to try to, generalize this to other situations, like instead of looking at the cube roots, maybe look at, 5th roots or something like that, or understand the general case or something like that.
Mm-hmm.
But in addition to generalizing that way, I think I may have suggested that, I think I did suggest that it would be interesting to sort of unify all these together, unify the special degenerate behaviors, understand how they relate to the generic behavior. And in terms of, maybe, I'm still not sure how to think about this, but I was vaguely thinking of, some moduli stack of general Z mod 3 torsors over the Eisenstein field or something like that. And perhaps there would be, like a moduli stack with orbits of different amount of isotropy or something like that, different kinds of isotropy subgroup or something like that. So there'd be some degenerate orbits and then a generic orbit or something like that. So I already suggested that idea very vaguely, and I still think it's a good idea, but there's something more interesting about that idea that I hadn't noticed. And it has to do with this whole idea that I don't understand yet, that for some strange reason, we're doing a bunch of linear algebra and functional analysis over Z mod 3.
What makes something be so great as to be called functional analysis?
Well,
with a two-dimensional vector space over a finite.
Right. I guess, right. Right.
But maybe in that sense, the functionals, is that what you...
That's interesting too, but that's not what I was thinking. What I was actually thinking, I just meant in the very naive sense that we have some interesting infinite dimensional vector spaces here. So that's really all I meant. So that was a very overblown way to say that we've got infinite dimensional linear algebra going on.
Like
I'm using functional analysis roughly as a synonym for infinite dimensional linear algebra. But on the other hand, I do suspect that there is actual interesting functional analysis in a sense going on here. It's a bit of a wild guess, but this whole idea of p-adic Banach spaces and stuff like that.
Well, okay, but
that's a wild guess.
Okay,
what were you going to say? Yeah.
So what's infinite dimensional in this business? You've been steering away from anything.
Okay, so let me try to say that. So let's take GL1 over the Eisenstein field, the Eisenstein rationals, or whatever you call them. And that is an abelian group. And I guess it's very close to being, because of the fact that the Eisenstein field or the Eisenstein integers has some, it's like very simple and nice, right? It's got like unique factorization because it's like a Euclidean domain or something like that. And that means that it's got unique factorization into primes in an appropriate sense. So this is close to being a free abelian group. I guess there's a little finite group of units, perhaps a Z mod 6 worth of units. But aside from that, it's mostly free on the Eisenstein primes. And but on the other hand, suppose we take this abelian group. So yeah, I'm now thinking of this as an abelian group. And as an abelian group, I'm tensoring it over the 3-element field. No, how do I say that? No, tensor it with the 3-element field. Let me undo my mistakes. Some of my mistakes here. Okay, tensoring it right. I guess I'm really just tensoring it over Z, which means I don't even have to say anything because that is the initial thing. But tensoring it with the 3-element field. And that results in an infinite dimensional vector space over this finite field. And I have a pretty good idea of what that basis is for that infinite dimensional vector space over the finite field, but maybe I'm being a little bit sloppy because I guess it kind of looked like it does have one extra dimension that I wasn't expecting for the units or something like that. But it has a basis element for each Eisenstein prime, I think.
So let's see.
And there must be all
Yeah.
sorts of slicker ways that people talk about this, but I'm, fumbling around inventing it for myself. So, this is some funny infinite dimensional vector space that you get from a number field, in particular over the 3-element field from the Eisenstein field in this example.
Just to be annoying, what
Yes.
happens with the 6-element subgroup you mentioned of GL1Q? So let's see, when we tensor that with F3.
I'm imagining that the number one is the negative one is getting killed off or something like that. -1 is getting, because -1 is order 2, so it's going to be killed off by,
Oh, I see.
by tensoring with the 3-element field.
Okay. So it gives us one extra.
I think, yeah, I guess it gives us one extra, which
Just sort of the units direction as opposed to the primes directions. Yeah.
yeah, but I don't really see how this would go, but it reminds me of the way Conway talks about -1 as a classical prime, or a non-classical classical prime. I mean, a prime over the rationals, and like that is, really that's just in the units group. It's a I'm wondering if this extra one that we're talking about, I'm wondering if that is an honorary extra prime, honorary extra Eisenstein prime in some sense. I have an argument that says it isn't, and I have another argument that says maybe it is, but I don't know. But it is there in this vector space, apparently. So we got hold of this vector space in a reasonably functorial way. And that means we can take, any old automorphism of this field. Well, I mean, there is basically only one interesting automorphism of this field, which is called, it's the thing we've been calling Eisenstein conjugation. And by functoriality, that acts on this infinite dimensional vector space by a linear operator. So we really are doing functional analysis. We've got a linear operator in an infinite dimensional vector space, and we're sort of interested in trying to look at its eigenvalues or eigenspaces, or its best approximations to its eigenspaces, or something like that. We're interested in analyzing how this linear operator acts on this infinite dimensional vector space. And I guess it's not quite diagonalizable or anything like that, but it does sort of, right? It sort of, you see what it does? How it acts?
This is Eisenstein conjugation?
Yes.
Yeah. So it acts as negation in GL1QE. If you think of GL1Q as, wait, why am I saying that? That's not true. No. I was thinking that since one of the cube roots of one is the inverse of the other, that was like negation if you think of it multiplicatively, but well,
I mean, there's like a real and an imaginary or something like that. It's like it's sort of like negative on the imaginary part, and
so I'm just trying to figure out how the
yeah,
Eisenstein conjugation acts on GL1, comma, Eisenstein field, and it seems like it's separately acting. So you said that thing is like, sort of has like one generator for each prime, Eisenstein prime, together with one generator for the units. And for some stupid reason, I started by accident with the units. And so the units form Z mod.
Oh, the units. Okay. Yes.
And so.
Yeah, I was totally forgetting to look at the units. I was just completely looking at the others, but go ahead. Yes.
For some idiotic reason, I started with like the smallest thing to study, which was on the units. So those are Z mod 6. So their Eisenstein conjugation is acting as negation. But then for the other Eisenstein primes,
yes,
I guess they're the ones that were the rational primes that didn't split in the Eisensteins.
right.
And then so this Eisenstein conjugation will fix those.
Right.
And then the other primes in the Eisenstein primes will come in pairs, I guess, that are.
That's right.
Eisenstein,
Eisenstein conjugate pairs. That's right.
And so those will get interchanged.
That's right. That's right.
So we can sort of. So when we tensor with F3, we can think of it more in terms of like the vector space situation.
All right, I have a really stupid question. How stupid of a mistake am I making here? So we're doing like linear algebra over F3.
Mm-hmm.
So it's like characteristic 3 or something like that. And some very naive, probably mistaken intuition was telling me that, like, you know, if we look at an operator of order 2, then that would diagonalize. but it's not diagonalizing here, is it? Let's see.
I think it should. I mean, the usual recipe for diagonalizing an operator of order 2 involves dividing by 2, but that's okay.
All right. So what are you telling me here? So I've got like 1 and then some Eisenstein prime P, and it's conjugate P prime. And then it's, you know, it's square, and of course its third power counts as the identity because we're modding out by cubes. And so P squared. So what's going on here? P squared. What is this? P squared, and this is P squared P prime squared. And so what are you telling me? You're telling me that this thing
So those are fixed.
Those are fixed.
And then the.
And you're telling me there are others that are like skew fixed or something like that? Is that what you're saying?
Let's see. Well, I must be.
So what does that mean? Like this one over here. P squared. So negative of that would be 2 times that.
Well, but you shouldn't say 2 times it. You should...
right. Okay, so that really means that it's squared. Right. You're complaining about the fact that I'm just horrifically mixing up additive and multiplicative notation, right?
We're not going to figure it out if we do.
But I think what you're saying is that, you know, P to the 4th P.
Yeah. So now the trick is that we could.
Yeah. So those really are. So you're right. So those really are eigenvalues, eigenvectors. So I guess it really is. Yeah, I guess it really is true that this does diagonalize.
So those 2 guys that you set circles around.
Yeah.
They are negatives or inverses of each other, right? So yeah. So,
Yes, or, since we're mod 3, they're also doubles of each other.
Yeah.
Um,
so they're anyway. So they're being anti-fixed, or whatever you call it.
So I guess it really is true. Maybe it should have been obvious to me that an involution over the mod 3, an involution really will diagonalize into a +1 eigenspace and a -1 eigenspace. And
I know just from abstract baloney that it happens to be true, because actually we were having like I was talking to a physicist.
yeah,
And he was saying, we were talking about bosons. Sorry, I'm going to digress for a while.
sure, that's fine.
Bosons and fermions. And he said, well, the reason why there's just these two kinds is that you have an operator, which I'll call P, that switches two particles of the same kind. And if you do that twice, that's the identity. And then he said, so it's squared, this operator squared is the identity.
Yeah.
And then he said, and this operator has to be self-adjoint. And so, which is wrong. He said that operator has to be self-adjoint. And so it's has to have real eigenvalues. And so these eigenvalues, when they square them, have to equal 1. So the only real numbers that when you square them equals 1 are 1 and -1.
Yes.
So those are the two options for what happens when you switch two particles. Either the phase gets multiplied by 1 or by -1.
And you think he's deliberately trying to trick us or trying to trick himself?
No, he's just not very good at math.
Oh.
He said, or mathematical physics or something. So I said, no, there's no reason this has to be self-adjoint. This isn't supposed to be an observable. I mean, it'd be cool if it was, but it's supposed to be unitary because it's a symmetry. So then I gave another argument, which was to say, like, it's unitary, so the eigenvalues have to be on the unit circle. So you're looking for numbers on the unit circle that when you square them give you 1 or give you 1.
Yes.
Those are 1 and -1.
Yes.
So it was self-adjoint after all.
Right.
But then I said, but if you're going to be like really nitpicky, that in infinite dimensional spaces, not every operator has self-adjoint or unitary operator has eigenvalues. It could have continuous spectrum.
Yes.
But then I said, but you don't even need to worry about that, because in fact, any operator on any vector space, if it has the property that you square it, it equals the identity, then it has a basis of eigenvectors whose eigenvalues are 1 and -1, because you can just take a vector and either average it with you can just do P plus, sorry, you can do your vector plus P times the vector divided by 2, the vector minus P, the vector divided by 2. And so nothing about unitary or self-adjoint or spectrum or anything is relevant here. It's just a thing about linear algebra that works in infinite dimensions. But I noticed when I was thinking about that yeah, you did need to divide by 2.
Right,
So
right.
That's why I was prepped for this conversation. Like, well, 3, everything. That's fine.
Somehow I hadn't even noticed that it was actually diagonalizable, but I guess it is. And so, I mean, so I'm saying it seems to be better, right? This viewpoint seems to be, I don't know what it means, but it's somehow telling us that this is better than just having 2 special ways in which the Galois group degenerates. It's actually telling us that somehow, we're diagonalizing an operator, and we're looking at the eigenvalues, and that one eigenvalue is corresponding to one very kind of special degenerate behavior, and the other eigenvalue is corresponding to this other very special kind of degenerate behavior. And I don't know what that means, but it's suggestive.
So so what is the deal with GL1, QE, tensor F3? Why is that group? What's the best way to say what's the point of that group?
Well, it has something a whole lot to do with classifying Z mod 3 torsors over the Eisenstein field. Is that?
Can you say what that is?
Well, I mean, it's this joke that we've been talking about cube-free numbers or something like that, right? I mean, we had the idea that the quadratic, or the Z mod 2 torsors, or the quadratic extensions, the quadratic fields, the quadratic number fields are classified by this, classically by the square-free integers or something like that.
So
I
can
would
I
have to
say
stop
that
and
this
think.
group
Yeah.
classifies Z mod, elements of this group correspond to Z mod 3 torsors over the Eisenstein field?
Something very much like that.
What is that?
I'm a little bit worried about this one extra basis element that I hadn't thought about, but it probably works out. And it works out not just for, silly numerological reasons. It works out because of this Tanakian viewpoint that we've been exploring. I mean, we still need to clarify how that Tanakian viewpoint works, but that's what's making this work.
Uh-huh.
Right, and let's just think about what one of the things that's suggesting. That's suggesting that our infinite dimensional vector space here is not just an infinite dimensional vector space. It's a categorified infinite dimensional vector space. This it's this monoidal groupoid of, or maybe is it a groupoid? I don't know. It's a monoidal groupoid of torsors of some kind. So we have a categorified infinite dimensional vector space.
Yeah, it'll be group. Well, it'll be a two group because torsors have inverses.
I guess that's right, and it may be, I don't know. This may be completely misleading, but it's what you're saying is suddenly making me think of what's that buzzword when people talk about the homotopy fields or something like that.
I don't know.
Morava
K-theories?
K-theory or something like that.
No, I don't know.
The Morava K-theory spectrum, don't people sort of jokingly call those things?
Yeah, I guess you're right.
Fields.
Field spectra.
Yeah, something like that. Because the linear algebra of the homotopified or categorified linear algebra over those ring spectrums is very straightforward, the same way linear algebra over a field is very straightforward. If I'm not completely misremembering all the facts and all the
that sounds, I never understood that stuff.
But now you're making me think that that's actually related somehow to what we're talking about, but I don't know.
So the automorphism group of every object here is just Z in this category, in this two group you're talking about, it's just Z mod 3, right? Because
that's right. That's right. So it sort of feels somewhat mildly categorified or mildly homotopified, but it still seems interesting that it is homotopified.
Do you think?
And again, I emphasize that you and me should really be trying to think about this in the Tanakian viewpoint, groupoids. Go ahead, yes?
Do you think there's any interesting Postnikov invariant of that two group, meaning that that there's like they're an interesting associator, or is it just sort of separately as
I guess I totally forgot to think about that. The whole thing is so abelian and so stable that it's hard to imagine
my initial guess is that no, there's nothing.
But I honestly don't know. And if we generalize it, there might be more possibilities. And but even if it does turn out to be completely free of any Postnikov twisting, it would still be interesting as a sort of homotopified thing.
By the way, you just reminded me at some point today, I do want to actually tell you something.
Okay, do you want to plan out how we're going to do that? Well,
I don't
I'm
know
still
where you
rambling
are in
on
this.
here.
I can
Yes?
wait till you're done with this stuff, of course, but I don't know exactly what this, how close you are to being done with this stuff, or what this counts as this
I'm
stuff.
hoping I always hope I can get through it very quickly, but I'm hoping I can get through it relatively quickly. So
I feel like you got through something just now, but
I did, but I have more rambling related to it to say. So, so what I'm trying to do is the stuff that we just sort of got through, I'm trying to mystically connect it to another, or perhaps the same sort of project that I've hinted at working on in the past couple of weeks. And right, and partially this is this cultural project of mine that, you know, I was so inspired some decades ago by this paper by B.F. Wyman. By the way, B stands for Bostwick, if that's of any interest to you.
no wonder he goes by B. Okay.
Well, I just thought it was fair. I've been calling Emma Lamer by their first name, so I figured maybe I should call Bostwick by their first name too.
You know if Emma is the daughter of the Lamer?
I've kind of been assuming so, or I've been assuming they're related in some way, but
Yeah.
Maybe I forgot to check.
Yeah.
It could be just, you know. Although I have a feeling there might be more than one famous Lamer, and you know, I can't be sure that Emma isn't one of the famous Lamers, but I think there might be 2 or 3. I don't know, because there's some D, right? There are some Lamers with a D initial, but I thought there might be more than one with a D initial. I don't know. So, right, in my original version of the story, right, it was like, you know, I always require heroes and villains. And for me, Wyman was the hero and Emma Lamer was the villain. But I've sort of revised that to some extent. I now think that they were both heroes. And I sort of associate them with these 2 different degenerate orbits. And that, you know, the project is to sort of right now it's increasingly like there are these 2 degenerate orbits, but it's not just that there are 2 degenerate orbits, it's that those 2 degenerate orbits, you know, because they're corresponding to these 2 different eigenvalues, they're sort of like complementary and they control the whole thing, right? The generic orbits should sort of be controlled by these 2 degenerate orbits in some sense.
So in what sense are these 2 protagonist people connected to those 2 different degenerations? I don't actually get that.
yeah, it's a little bit right. It's a little bit tendentious, and one of the problems is that, you know, as I read both of their papers, I realize more and more that they're both really saying the same thing. They're both agreeing, and that they're just having a stupid argument over terminology. I think they really are arguing over the meaning of the terminology reciprocity law. And you know, they're both agreeing that it's interesting when you have literal reciprocity laws, literal old-fashioned reciprocity laws, and they're also both agreeing that it's very interesting when you don't have those and you have to try to invent something new.
Yeah.
But Wyman's attitude is that the new things, you're probably going to end up calling those reciprocity laws anyway, even if they don't qualify as literal-minded reciprocity laws in the old-fashioned sense. And I think, and my argument for why Wyman takes this attitude is because I think he basically makes it Shimura's fault. You know, Shimura is a famous great mathematician, and Shimura started talking about these, you know, non-solvable reciprocity laws and things like that, which probably are not reciprocity laws in the old-fashioned sense. But, you know, what Shimura says goes. So I think, Wyman says, well, that's what Shimura is. That's how Shimura is talking. So we're going to call these things reciprocity laws too. Whereas Lamer is insisting, no, a reciprocity law is a reciprocity law. If you've got something new, you admit that it's not a reciprocity law and you study those things instead. And so for both of them, the new things are interesting that maybe aren't really reciprocity laws. The new things are interesting. And they seem to be, kind of little tips of the iceberg of the Langlands program. It was, or like sort of some people say that the Langlands program started out as a dream of inventing non-abelian reciprocity laws. But, then you can argue that, well, the non-abelian reciprocity laws aren't really reciprocity laws.
Yep.
So right, but I'm still trying to answer your question about why do I blame one of them for this degenerate orbit and the other one?
Okay, sorry, you lost me. Okay, so I still don't know. Yeah.
Right. Why
one of them has anything more to do with?
Right. Well, because yeah. Because I learned the abelian class of field theory, or I that's where I started to learn abelian class field theory from Wyman. So I associate Wyman with the abelian stuff. And so that means, the ones where x squared is equal to x bar or something like that. That's that degenerate orbit. Whereas from Lamer's paper on rational reciprocity laws, and at some point we should bring this up on the screen, but maybe not today. I'm not sure I'm competent enough to bring it up on the screen today. But yeah, so Lamer's paper, the one that's sort of a tirade.
But he's the off-diagonal guy. Is that right then?
Well, I'm
Wait,
I'm a little bit worried that there's some funny reversal of which one is the diagonal and which one is the
x squared equals x bar.
Yes.
The off-diagonal elements. They're the night move elements in this.
They are the night move elements, but they're also the ones that somehow end up being the abelian ones. So there's some funny reversal here. I can't figure it out right now. Maybe you're just, don't get angry at me about this, but there's some funny reversal here going on. Like, right, the diagonal.
Why would you think that
what?
Is there some reason why you think the diagonal is more abelian?
Well, yes, because I've got this wreath product picture where Eisenstein conjugation. So is there some explanation why are we getting things exactly backwards now?
Wow.
I mean, I'm willing to not worry about it now because it's got to work out somehow. If you can explain it to me right now, that'd be great. But are you trying to explain it to yourself?
I'm trying, but I'm confused. Yeah. What did you do?
Well, I somehow managed to get it exactly backwards. I got it exactly backwards, but.
Well, you said maybe you just asserted it. You asserted if x on the previous page, if x squared is equal to x bar up to cubes, you get an extension with an abelian Galois group. And that's what's making things come out.
No, that's actually right. I mean, if x is equal to x bar, that's the one that gives you the non-abelian things. Look, I don't have the explanation for this, but there's got to be an explanation for it, and the explanation for it is probably intertwined with my undone homework assignment, where I'm supposed to actually explicitly work out the reciprocity laws and exactly how they work.
I think so. I think part of the problem is that one of your little 3x3 squares is a picture of, well, it's sort of like it's a picture en route to describing a Galois group.
Right, right.
It's the Z3 times Z3 part of a Galois group.
Are you saying that one's like a homology group and one's a cohomology group? Or are you saying something
Well,
like
I don't know. So that one's like a Galois group, whereas this other thing, the thing that you have on top of the page here,
Yeah.
that's I mean, that's not supposed to be a Galois group primarily. It's supposed to, maybe it winds up being a Galois group, but it's actually like a group of
Yeah.
Z3 torsors.
Well, yeah, that's right. I think it really is a matter of homology groups versus cohomology groups. The homology groups are the sort of abelianized Galois groups. And the cohomology groups are these groups of torsors.
Yeah.
And that still doesn't explain why it's coming out.
No,
backwards.
unfortunately, it still doesn't. Yeah, that'd be like vector space duality. And that shouldn't switch the diagonal with the off diagonal. Yeah.
Yeah, but I'm saying I don't want to resolve this question right now. I don't think it's going to be difficult to resolve. It's obviously important to resolve.
Okay, fine. That's fine. I mean,
so
not
yeah,
that you don't want to. It's that you have no clue.
that's right. That's right. That's right. And I want to say some other stuff, and I want to give you a chance to say some other stuff.
Okay.
So.
Yeah. Well, it's good that I pressed you on why one of those people corresponds to the one and one corresponds to the other.
Well, yeah, but right, but right.
Okay,
but, I mean, somehow it has to do with the fact that I associate. Right, I learned abelian stuff from Lyman. On the other hand, just in the past week, learning from Lamer's paper, I've been sort of learning this interesting, mathematically very interesting, but also historically interesting bit about how Gauss and Jacobi. Lamer doesn't actually mention Gauss, but I think Gauss did like one case or something. And then Jacobi did something like up to the number 37 or something. He did something, which is there some famous factoid about the number 37? Is it like the first prime where some.
The first irregular prime? No, I don't.
Something like that. I don't know. Maybe I'm completely wrong in thinking that that's why Jacobi stopped at the number 37 or something like that. But apparently Jacobi, according to Lamer says it's a very, back then it was a little known paper of Jacobi's that Jacobi wrote down a bunch of these Frobenius patterns, these non-abelian Frobenius patterns. So in other words, it looks like, Jacobi was doing a little bit of the proto-Langlands program, if I'm not misunderstanding too bad.
Let me just take over the screen for just 1 second.
Sure, go ahead.
Really, what I want to do, which I want to show you. Hey, sorry. I want to. Damn it! Oh, here, I'll take it. Sorry. This.
Yes.
This is not what I want to do. God damn it! It's so hard to manipulate this. I had. So, what is the first irregular prime? 37. So those are the primes that Kummer couldn't prove Fermat's last theorem for because they have some thing going on. Yeah. Anyway,
yes.
So
I have no idea. Yeah, I'm guessing that's not related to why Jacobi got tired at the number 37. I don't know if he got tired right before the number 37 or right after the number 37.
This is like huge debate. Did you know about like why some Greek guy the square
root of 2
numbers are square root of 2, square root of 3,
right?
Up to 17.
And because they were using some fancy continued fraction.
I've heard that's one theory. I've seen like different theories. Yeah.
Oh, I didn't know there were different
which are probably better than others. Yours is probably
better. Well, I mean, it could be that the theories are secretly isomorphic to each other.
Well, I don't know. That sounds unlikely. You got to share your screen again if you want me to.
Okay, I'm hoping this is gonna work. I'm hoping the thing isn't screwed up now. So share screen. Whiteboard. Hope that works. Now you're seeing the whiteboard again.
Yes.
Okay, and right. So I did sort of say, you asked me why do I sort of say one of them with the one degenerate orbit and the other with the other, or one with one eigenvalue, one with the other eigenvalue. And it's because I learned abelian stuff from Wyman, whereas I got some interesting hints about non-abelian stuff from Lamer.
Uh-huh.
And so right now I actually am very close to stopping talking, so you might actually have time to say stuff if you want, but I'm not quite done yet. So what I'm trying to finish up here with is that, well, like I said, it seems not just that there are these two isolated degenerate orbits or something like that, but they actually control the generic stuff as well. And I think the way in which they control the generic stuff, I think is going to be sort of very straightforward. I think, what am I trying to say? That, I mean, we've been talking about this, cohomology group of torsors. And of course, as a cohomology group of torsors, it's in some sense, a categorified or homotopified cohomology group, at least slightly.
Mm-hmm.
And in particular, that means that it is a cohomology group. And that means that, these Frobenius patterns have the group operation on them. Whereas the splitting patterns, it's less clear how to combine two splitting patterns to get a new splitting pattern. But it is clear how to, you just multiply, or maybe you call it, depending on whether you're thinking additively or multiplicatively, you multiply or add together two splitting patterns, two Frobenius patterns. So there should be like, some Frobenius pattern. I think it should just work like you have the Frobenius pattern for, cube root of X and the Frobenius pattern for the cube root of Y. And you should just multiply them together to get the Frobenius pattern for the cube root of X times Y. And I think that's the way it should work.
Uh-huh.
And so the abelian ones should multiply among themselves. So that's corresponding to one of the degenerate eigenvalues. The other ones don't multiply among themselves because it's abelian. It's like a non-abelian cohomology set or something, I think. I'll have to think about that. But you could still have the abelian ones act on the non-abelian ones. So in other words, you can sort of blend together the abelian ones and the non-abelian ones.
Uh-huh.
And maybe that will be enough to, so right. You take an arbitrary Eisenstein quantity and you multiplicatively decompose it into two of them, one of which will be the abelian kind, the other of which will be the rational kind. And you can look at the splitting behavior for either of them separately, and then you should be able to just combine them together, I think, by having the abelian one act on the non-abelian one or something like that. So what I'm trying to say is that this seems to me to be giving us a lot of good raw material, raw data for trying to learn the Langlands program. And I think I've vaguely heard rumors. I think Lawrence Gunnarsson actually gave me a paper some years ago where somebody actually used this approach to teaching the Langlands program. So I really want to go back and get hold of that paper again. I mean, this paper that I'm vaguely remembering referenced Gauss rather than Jacobi. But I think it seems to me that, there's a whole bunch of data here that I think might be giving us not just isolated examples of the Langlands program, but very easy baby examples of the Langlands program, of not sort of, you know, so to speak, non-abelian reciprocity laws, and not just isolated examples, but a whole bunch of them having to do with all possible cube roots of Eisenstein numbers. And, you know, and the vague rumor is that, well, these non-abelian reciprocity laws in these examples, they have something to do with, you know, they're not just congruence patterns. They're not just congruence patterns, but instead they involve quadratic forms, which numbers are represented by certain quadratic forms or something like that. So I'm suggesting that there should be a whole lot of raw material to try to learn the patterns here by looking at all these different examples. I mean, one of the things I'm very tempted to do is I'm very tempted to just, you know, try and guess the patterns by myself. Start looking at cube roots of, you know, any old integer, for example, and try and look for what primes it splits and for what times it doesn't split.
Mm-hmm.
Or maybe there's even an extra orientation bit of information there, giving a Z mod 3 torsor, and trying to interpret this data in terms of, according to rumor, something about quadratic forms, something about being in the image of some quadratic forms or something like that.
Mm-hmm.
Trying to remember whether they're ternary quadratic forms. I have a feeling ternary quadratic forms are involved. I don't know, but that's my vague idea. That's my vague idea. I think I'm sort of done now. Yeah, so that last punchline that I sort of tried to end with was just the punchline of, it looks like there's a bunch of interesting stuff here to try to learn here. And in particular, you know, I could try to learn it from readings from papers, but I could also try to learn it just by, you know, my stupid method of trying to reinvent it for myself by looking at a lot of data.
Yeah. So okay.
So I'm sort of done now. You have stuff to say now?
Yeah, I have some stuff to say. So one first thing I have to say is I really want you to get to the Artin reciprocity theorem, and part of why
Yes.
I really want to is because when I'm trying to very feebly trying to learn about it myself, the
Yes.
parts of it seem quite elaborate, and so I'm wondering whether you are like
On the right track. Yeah.
skipping the proof part and just like stating the theorem in a really elegant way, or whether you like actually like.
I think we're going to
figure out how to
actually be
prove
seeing the
it,
proof.
or-
I think we're going to actually be seeing the proof, but we'll see how it goes.
Yeah, so I'd love to see a proof or something close to a proof, because it might be nicer than
Yeah,
stuff so far.
just one silly buzzword I want to mention here. When I was trying to decipher Lamer's paper, and again, Lamer was mentioning all this historical stuff. One of the magic buzzword that was showing up was something called period equation. I don't know. It made it sound like, I don't know. Made it sound like I have to learn about something called a period equation. I don't even know what that is yet. But it reminds me when you're telling me about stuff about period, or somebody's telling me stuff about periods, like a magic buzzword that people talk about in, I don't know.
Okay, well, there are periods in algebraic geometry, but those are
This might be completely different. I don't know.
I hope so, because that's weird if it is the same.
Okay, but I sort of interrupted you. Do you want to keep on going here?
Yeah, I want to say something a little more different.
Okay.
So I like this paper, Brouwer has another term, historical perspective. It's really long, like 92 pages long, and it's very historical. And so it's about these folks' classification of, they were trying to classify division algebras over the rational numbers, or more generally over number fields.
Yeah.
And it involved determining whether division algebras split over various fields, so like when you tend to go up to some larger field, whether they become a matrix algebra. And then Hasse had this what do they call it, the Hasse principle? I don't know.
It says local global here or something. Is
Yeah,
that
the local global principle. Yeah. So in this example, it works in the sense that
I mean, that also sounds like descent. That sounds like the descent thing that you were talking about, local global.
Right.
Is that the right idea?
Yeah, well, it's a little more, yeah, that's right. It's sort of more fancy because so the principle is that, yeah, it should be related. The principle is that a division algebra, or more generally one of these central simple algebras, will split over your number field if it splits over each prime. So you can localize and split. So that's one of the things they showed to get the job done.
Well, that's interesting. Okay, yeah, that's right. That is sort of a fancier version or something. Okay, go ahead. Yeah.
So there are a couple of things I want to mention about this. So one thing that's sort of interesting is there's this business about the Brouwer group and class field theory and cohomology. And the only thing I wanted to say about that was something. So like we've said that, like, sorry, my computer's starting to stagnate here. We've said repeatedly that like cohomology is often used as a tool when you could use category theory and understand things more thoroughly.
Yes.
And so what's interesting here is that, so they wound up classifying central simple algebras over number fields, and part of it was the idea that of this Brouwer group, where you classify central simple algebras up to Morita equivalence, basically.
Yes.
And so those equivalence classes form a group under tensor product, and then they identify that group with a certain cohomology, set cohomology group. And so one thing that's interesting here is it says, well, so like Emmy Noether was working on this stuff. One of her theorems is now seen as the vanishing of the first cohomology of some Idel class group. I don't even want to get into that, but I like this paragraph here. In the course of later developments, the idea of approaching class field theory for Galois extensions by means of factor systems. So factor systems, which I will talk about, are like an explicit way to build a central algebra from a two co-cycle.
Yes.
You'll see it's like very familiar to you when I discuss. And so yeah, okay, this is the part of the sentence I really wanted to read. While Hasse had introduced simple algebras into class field theory, so that's sort of what I'm talking
I mean, did you finish reading that previous paragraph? I mean,
I didn't want to talk about, yeah, no, that's
okay. You can skip over that. Go ahead.
No, I was interested in the erasure of the use of simple algebras. So while Hasse had introduced simple algebras into class field theory, these have survived in modern times as second cohomology classes only. So the fact that you can get these central simple algebras from the second cohomology classes is like supposedly not used in class field theory now. You just use the second cohomology group to itself. So that's sort of like exactly what I want to go against.
Sure.
And maybe I'll tell you, like, something about it. So every central division algebra, so central division algebra over a field, that means like the field is the center of the division algebra. So it's like not the opposite of a field extension, where the center is the whole extension. Division algebras are the quaternions, are a central division algebra over the reals. Every central division algebra over a number field is cyclic or of Dixon type. And what I'll show you is that this cyclic kind means that it's a twisted group algebra, a twisted version of a group algebra, where the group is the Galois, is a Galois group.
Yes.
Or actually it's like a cyclic Galois group. Yeah.
Okay.
So here we go. So suppose you've got L is a cyclic extension of a field K. So
yes.
I guess it's a finite cyclic group with n elements, and let sigma be the generator of the Galois group.
Yes.
But then we're going to build a central division algebra over the little field K from this data, and a bit more data. So the idea is we're building an algebra over the little field K, and it's going to be generated by the field extension L, and then one extra element, U, and maybe
sorry, I just lost track. What is L? Could you go back for a second?
L is the field extension, a cyclic extension.
Oh, okay. Okay, yes. Okay. So that's interesting. Okay, so you're going to have a commutative field extension, and then from that you're going to get
a non-commutative division algebra
with the help of U or something. Okay, go ahead. Go ahead.
Some stuff, yeah.
Yeah. Okay.
I want to take this thing A here to be 1 to keep things simple.
Okay.
So we're going to look at the algebra over the little field generated by the field, and one extra element U, whose nth power is 1. So if that's making it sound like well, if you just saw that, you might think, oh, he's about to describe like the group algebra of the cyclic, some kind of algebra
right.
with a cyclic group, but not with coefficients in K, but coefficients in this larger field L. However, it's going to be twisted in this in a couple of interesting ways. The first is that this U guy doesn't commute with guys in the larger field L.
Right.
So when you commute it past a guy X in the larger field, this X to the sigma means you apply an element of the Galois group that's this generator of the Galois group that's a So that's good, because it means that like if you commute U to the n past X, it's like commuting U past X n times, then you're gonna hit X Galois transformation n times, but that Galois transformation, when you do it n times, you're back to the identity.
Yes.
So that sort of makes it compatible with U to the n equals 1. Because you know that when you pass 1 past X, it doesn't do anything.
Yes, I think I'm following.
So far that is a sorry. Let's see. maybe that's, sorry, let's see, maybe that's all. Sorry, I thought there's some more stuff. Okay, no, there's no more stuff here. So then they're claiming that's a central simple algebra over your little field. So it has dimension n squared, because you can think of it.
I mean, that makes it sound like some sort of twisted matrix algebra or something like that, in some very vague sense of twisted. But what?
Yeah, so all these central simple algebras will have dimension that's a perfect square.
Uh-huh.
Because you know that when you like, well, this is not a good explanation, but it's true that when you like go to a big enough field extension, they become matrix algebras, and then they have to have dimension n squared.
Yes, yes. If you tensor with the algebraic closure, yes.
Yeah. But also we can see it has dimension n squared, because the way I think of it is like, we've got this Galois group that's a cyclic group with n elements, and we're sort of looking at this algebra that we're talking about. It's sort of like the group algebra of that. So it's like functions. I'm going to think of it as like functions on that n element set, but they're functions valued in this bigger field K that has
Yes.
n.
Yes,
So you get like
yes.
an n tuple of vectors of size n, so it has n squared.
Yeah, there's something suggestive about that, but I'm not sure I really see it yet. But go ahead, yes?
So anyway, so you get central simple algebras that way. And these are called cyclic algebras. Now, there's a weird thing that it's sort of harder for me to interpret, which reminds me a lot of some things you've been talking about, which is
Yes.
you could also, instead of u to the n equals 1, you could say that u to the n is any invertible guy in your little field.
Yes, yes.
That reminds me of this stuff of like q up to cubes. Or,
Yes, yes.
yeah. And so that's a cool idea. And then it seems to be that there's like a souped up version of that idea called factor systems that was invented by Noether,
Uh-huh.
which is really, which I'm trying to find the definition of. And these factor systems, they're really co-cycles. They're really two co-cycles, I think. And so the idea is you can like soup up, you can soup up the construction I just described. Maybe these are too many formulas for your brain to absorb, but
it's okay, sort of.
So instead of like looking at different powers of this element that I was calling U, that's like the generator of the cyclic. We put in a bunch of them, one for each element of the Galois group. And then we say we multiply them in this twisted way. So U times sigma times U sigma times U tau is U sigma tau times some fudge factor, which can be any invertible element in our little field. And so what we're doing is we're taking that, the thing before that I described was just a group algebra, but it's a group algebra of the Galois group with coefficients in the field extension. And now we're going to twist it in the usual cohomological way by sticking in a 2 cocycle. So you stick in these fudge factors, and then you figure out what the fudge factors need to obey to make the multiplication be associative. And so you get this disgusting looking equation called the associativity relations or Noether equations. But what those are is just like what you have studied before yourself, is like the conditions that you need to get associativity. So that's a 2 cocycle condition in modern jargon. So this is like where Noether had invented, I guess, like 2 cocycles for on a group. with values in a module of that group,
Uh-huh.
because the Galois group's acting on the larger field.
Right.
So she developed it in her Göttinger lecture from 1929 to 1930, but she never published it, as so often the case with. And then they figured out, like, when a cocycle was a co-boundary. So in other words, when the twisting doesn't really do that much. So then they said the factor system splits. Let's see, maybe now it says that today we view the group of factor systems, mod split ones, as the second cohomology group, here it comes, of the Galois group G of your field extension in the multiplicative G module of the invertible elements of the bigger field. So H2GL star. And then finally, the upshot of all this is there's an idea, but this is like a relative Brouwer group. This is the Brouwer group of central simple algebras over K that's split when you extend to L. So that's a sort of nice refinement of the Galois group. It's like all the central simple algebras. They all split over the algebraic closure, but this is like getting both of them into the game. So Brouwer LK is the same as the second cohomology of your Galois group with coefficients in L, in the invertible elements of L. So that's pretty interesting to me. I mean, so this is the part this is the part of the stuff they're doing that I find easy to understand. Although it's still pretty cool to think about. For example, I would like to, I haven't really thought about examples of it at all, except for like the reals and the complex numbers, right? Where I know that, like, the quaternions you can think of as a twisted group algebra.
Right.
But I would like I've been thinking a whole lot about Clifford algebras and such, and that has a whole lot to do with Z mod 2, and that rises a lot from the fact that the Galois group of the reals, the absolute Galois group of the reals, is Z mod 2. And so I would like to do some example where you have like some other Galois group. And see what these division algebras actually are like.
Yeah, I'm just idly trying to figure out what the things you're describing are reminding me of. I was thinking of something about Clifford algebras, but go ahead. Yeah.
Well, I'm mainly like thinking about this stuff in Clifford algebras these days. I'm supposed to give another talk on the tenfold way, and the second talk is supposed to be about symmetric spaces in the tenfold way, and I think I've figured out tons of stuff about that. But sort of kind of vaguely connected to it, well, not so much for my talk, but in general, is this Brouwer group stuff and super Brouwer group stuff. But I thought of it like another thing that would be fun to think about, which I don't know if anyone has thought about.
Yeah.
Which is just a really simple idea for us, is that, like, instead of looking at H2 of the Galois group with L star, or the L, whatever you call it, you could look at H3. You'd get, I've thought about that stuff from the point of view of mathematical physics. So then you'd be getting two algebras, which are like a two vector space,
right,
with a basis given by the elements of the G, but we make it into a two algebra. So we give it a
Yes.
tensor product that's really just coming from multiplication in G, but then we twist it by twisting the associator. So with a third cohomology class,
Yes.
coefficients in L star. And so I mean, I think that should work very easily. And I'd thought about, I mean, people in mathematical physics have thought about that kind of thing for like building topological quantum field theories and so on. But the difference is that now, instead of taking a finite group and then like using the complex numbers as your field that you're using to build all your algebras, you could like look at a Galois group,
Yes.
but then like let it be the Galois group of some number field, and then like let it be acting as acting on some extension of that number field. And so you'd get some kind of interesting sort of more number theoretic version of these two algebras. I have no idea where I would go with that idea. It just seems like there should be lots of fun ones. I think I would start with the not so exciting one of just like the reals and the complex numbers. I think the way it works, right, is that like so then the Galois group is Z mod 2. And then maybe it would not be interesting. I'm forgetting like what the cohomology group of Z mod 2 are with coefficients in, these would be like with coefficients in something like the circle group. There's some, I guess if you do the cohomology of Z mod 2 with integer coefficients, you get Z mod 2, Z mod 2, Z mod 2. Going on forever. But I guess if you do it with coefficients in like the invertible complex numbers, then you only get like and it's not so interesting. I can't remember.
We're probably supposed to know the answers to some of these, but
yeah, once I used to know I mean, these are, yeah, we used to even talk about this, but this, like, I mean, this is known stuff. So anyway, maybe that example is not going to be interesting. Maybe I have to go to a fancier example to get an interesting two algebra extension of the real numbers. But anyway, this subject is fun, and this whole paper is like really interesting for both. I'm struggling to learn the math, and it explains a lot of the math, but there's still a lot of it that's hard to understand just from this discussion. But then there's also like lots of historically.
Yeah, it sort of looks like there's something.
It gets really, it gets really deeply into the details of like how these people figured stuff out. There was a little conference that they had, a little workshop these people had to work on this stuff. Trying to find it. Here it is. This is like the little program of the workshop in 1931. So it had Assa starting out by talking about these Dixon skew fields, these division algebras, and Brouwer talking about the Galois theory of skew fields, and Düring, who I think I've heard of, then Noether. So the word algebra was not used at the time, so she called them hypercomplex numbers.
Right.
So hypercomplex structure theorems and number theoretic applications. And then some other folks, and I guess they're all somewhat known folks. I've never heard of Archibald before. But so it's interesting. They were like
Okay, this is one. Sorry, I had claimed that I was better at being able to save the whiteboards, but I'm trying to make sure I'm saving the right whiteboards correctly here. Let me. I'm going to try to. Yeah.
Uh-huh.
I'm going to try to. Yeah. Go ahead.
I got a whiteboard because remember this time I was the one who started the Zoom or something. So
Yes, but
Zoom gave me a whiteboard.
right, but let me can you just try stopping your screen sharing for a moment, or maybe I should just go ahead and turn mine on. Let's see.
Should I stop recording? Is this getting boring?
Well, are you almost done talking yet?
Yeah, I could be. Yeah.
Can you go back later and clip off this boring part at the end off?
I sometimes can. Yeah.
I mean, because all I'm trying to do at the moment is I'm just trying to make sure that I correctly save the whiteboard. And let me okay, it looks like I've just got 2 pages. And right, there's not actually that much to lose. But I've got 2 pages. I'm just trying to make sure I save them. Let me try to save them.
Oh, no, I don't have the whiteboard. I have the chat, which was useless junk.
Okay, but I have the okay, it says let's see, that's not what I wanted. Let's see. Let me try again. Am I doing this right? Just give me a second. Save as PDF. Okay, let me try that. Now let me try saving. Show in folder. All right, I think it got correctly saved. Yeah. I'm still at the point where I'm paranoid about trying to make sure that things are saved, but I think it did get correctly saved this time. And I hope you can just clip off this end part. And
yeah, it's easier to clip off an end. It's harder to clip out the middle, maybe. Yeah.
Right, and right, which makes me think
boring things from now on.
Yeah. So all right, so we're just gonna leave it at that, and okay. All right, so I think I'm ready to quit.
Can you mail me the whiteboard stuff?
I can. I should be able to do that. But like I'm always a bit of a klutz at this. But yes, I will try to do that pretty soon. Pretty soon, I'll try to do that.
Okay.
Okay. So thanks a lot.
Yep. See ya.
I'll see you. Bye.